കാണാൻ പറ്റുമല്ലോ അല്ലേ? സ്ക്രീൻ കാണുന്നില്ലേ?
കാണുന്നുണ്ട് സർ.
ഓക്കെ. So today we are discussing the existence and uniqueness of Laplace transformation. Now here we consider a function small f of t, and we will restrict like this: mod f of t less than or equal to m into e raised to kt, where m and k are some constants and t is greater than or equal to 0. So we use this restriction, and we will prove two theorems. Okay. First theorem is existence theorem, and so the theorem says that if f of t is defined and piecewise continuous, not necessarily continuous, it can be piecewise continuous on every finite interval on the semi-axis t greater than or equal to 0, and satisfy that restriction. That means mod f of t less than or m into e raised to kt. So if it is satisfy equation number 2 for all t greater than 0 and some constants m and k, then the Laplace transformation L of f exists for all s greater than k. So if the function f of t is piecewise continuous and it is satisfy the equation 2, that is restriction, for some constants m and k, then Laplace transformation of function exists. So that is the theorem. So let us prove this theorem. You know, f of t is piecewise continuous. That is, we are assuming in this theorem. So continuous function that is integrable, e raised to minus st f of t is integrable over a finite interval, okay, on the axis t greater than or equal to 0. And moreover, you know the expression, what is L of f? L of f is nothing but integral 0 to infinity e raised to minus st f of t dt. Okay, so what is mod L of f? That equal to modulus of integral 0 to infinity e raised to minus st f of t dt mod close, that less than or equal to, you know, the property of mod. We are applying the property of mod, and then it is less than or equal to integral 0 to infinity mod f of t e raised to minus st dt, but we have put restriction to mod f of t, that is, we can substitute the bigger part, that is m into e raised to kt, then it will be less than or equal to integral 0 to infinity m into e raised to kt e raised to minus st dt. We can pull it, that is, m can be taken outside, m into integral 0 to infinity e raised to minus s minus k. Instead of kt, we can view it as minus of minus kt. That means s minus k into t minus e raised to minus bracket s minus k into t. Okay, so dt. So 3 മണിക്കല്ലേ? 3 മണി. ആയിക്കോട്ടെ. ഓക്കെ. അന്നിരുന്നിടത്ത് വരാം, കുഴപ്പമില്ലല്ലോ. ആ ആ ആയിക്കോട്ടെ. ഓക്കെ, ശരി. ഓക്കെ. ഓക്കെ 3 മണിക്ക് പറഞ്ഞിട്ടുണ്ട്. ശരി. So that is, so after integration we will get m into 1 by s minus k into e raised to minus s minus k into t from 0 to infinity. That will be simplified like this: m into m divided by s minus k. Okay, so this is a positive number. M is a positive, s minus k, since s is greater than k, m by s minus k is a positive number. So modulus is less than or equal to a positive number. That means this L of f exists. That is finite. L of f is finite. So the existence of Laplace transformation, that is we consider here. Okay. And now we go to the uniqueness part. You know that this integration exists, so we can say that the uniqueness using the integration theory. We know that if f1 and f2 are two functions, both are integrable. Okay, both are integrable. F1 and f2 are integrable. Then integral f1, integral e raised to minus t f1 equal to integral e raised to minus s2, integral e raised to minus, I will write that, integral we can put, suppose f equal to g, then that implies integral uh, 0 to infinity e raised to minus st of t equal to equal to g implies both Laplace transformations are equal. Okay, so that is so we can say the uniqueness of the Laplace transformation. Okay, so that is the result. So we have some exercise. I think you have done some of the problem. You can do this problem from 25 to 32. Okay, you can do these problems, inverse Laplace transformation. I think we have already done one problem, and similarly you can do all these problems, and there are problems in 33 to 45. You can try these problems also. That will give you more in-depth knowledge on this computation of Laplace transformation and inverse Laplace transformation. Usually we can see this type of questions in UGC CSR examinations. At least 1 or 2 questions you can expect. Okay. Now we move to another result, that is Laplace transformation derivatives and integrals. Okay, because sometimes we in mathematics we have to solve differential equations. In differential equation you can see that first derivative, second derivative, and higher order derivatives, and we have to solve, we have to find out the solutions of the derivatives or different form of the different functions of the derivatives, first derivative, second derivative, etc. So we have to find out the solutions for the differential equations. That is actually the theory of differential equation and partial differential equation in mathematics. In mathematics MSc, they are studying a theory that is differential equations. Okay. For finding the solution of the differential equation, the Laplace transformation technique is a good tool. Okay, you can see in this book also very fundamental ideas of differential equations and method of finding solutions. I think the students from BSc Mathematics might have studied the differential equation at least in a uh, basic level. This book contains all that basic information on finding the solutions of differential equation. So the Laplace transformation can be used as a tool for finding solution for the differential equation. So we are studying that tools based on this theorem. Okay, we have 2, 3, 4 theorems. So first theorem is Laplace derivative. The transform of the first and second derivatives of f of t satisfy L of f dash equal to s into L of f minus f of 0, and L of f double dash equal to s square into L of f minus s into f of 0 minus f dash of 0. So how can we find out this formula, or what is the proof of this formula? We have to find out the proof. So formula 1 holds if f of t is continuous for all t greater than 0 and satisfy the growth restriction that we have discussed in the beginning of this class, equation number 2, and f dash of t is piecewise continuous on every finite interval on the semi-axis t greater than 0. Similarly, for the second derivatives, equation 2 holds if and only if f and f dash are continuous for all t greater than 0 and satisfy the growth restriction, and f double dash is piecewise continuous on every finite interval on the semi-axis t greater than or equal to 0. Okay, so this is the theorem which gives the Laplace transformation of first derivative and second derivative. Similarly, we can apply this theorem again and again to the derivatives, and we can obtain the Laplace transformation of the higher order derivatives. That will be discussed in the next theorem. Okay, so let us go through the proof of the theorem. So here we have f dash is continuous. Okay, so let us try to find out the Laplace transform of f dash. So what is L of f dash? L of f dash is equal to integral 0 to infinity. It is not minus, it is equal sign. Integral 0 to infinity e raised to minus st f dash of t dt. Okay, we can integrate. Let us take the first function e raised to minus st and second function as f dash of t. So first function into integral of second, that is e raised to minus st into f of t from 0 to infinity minus integral 0 to infinity. What is the derivative? Derivative of first function? Minus s into e raised to minus st. So that minus is taken outside, and minus get cancelled, and it become plus, and s is coming outside. So e raised to minus st. Then integral of second function, that is integral of f dash, that is f of t dt. Okay. So, but the second time, in the second time, you can see the Laplace transformation. This is the Laplace transformation. S into Laplace transformation. Okay. So what will be the result? This is L of f dash is equal to s into this side, and we can put infinity and 0 here, and then we can see that if we put infinity, it will become 0. If you put 0, it will become minus f of 0. Okay, 0 minus f of 0. So the first term is minus f of 0. Second term is nothing but s into L of f. So you will get, what will be the step? L of f dash equal to minus f of 0 plus s into L of f, right? So what is excited? This can be rearranged again. Okay, so this can be rearranged like this. We can put this term at first. Okay, so what is the result? L of f dash is equal to s into L of f minus f of 0. So we can again find the derivative of second derivative. So what will be the second derivative? So you can use this formula for finding second derivative, second derivative. So we can put double comma single element, sorry, instead of f it will become f dash. So we replace f with f dash and f dash with f double dash. So this will be the step. And you know what is the step L of f dash? We can put the formula for finding L of f dash there, and we can take this one. We can put in this part. Okay. Instead of this one, we can put. So what will be the result? So this is equal to this is exactly L of f into s into f of 0, then f dash of 0, right? So this is the, yeah, this step is given here. S square L of f minus s into f of 0 minus f dash of 0. So this is the Laplace transformation of f double dash. Okay, so we proved this theorem, and now we generalize this result. Suppose f dash etc f raised to n minus 1 be continuous for all t greater than 0 and satisfy growth restriction in 2 for these functions and its derivatives. Then furthermore, fn be the piecewise continuous on the every finite interval on the semi-axis t greater than 0. Then the transformation of f raised to n is satisfied. L of f raised to n equal to, we can iteratively derive this formula also. Okay, L of f raised to n equal to s raised to n into L of f minus s raised to n minus 1 into f of 0 minus s raised to n minus 2 into f dash of 0, etc. f raised to n minus 1 into 0, f raised to n minus 0. Okay, I think you got the idea. Let us look at an example. Example 1. Take f of t equal to t into sin omega t. Then f of 0 equal to 0 because sin 0 is 0. Anyway, t is, when we put t equal to 0, this function will be 0. F dash of t is equal to sin omega t plus omega t into cos omega t. So f dash of 0 is equal to sin 0 0. The second term is also 0. So f dash of 0 is equal to 0. F double dash of equal to f double dash equal to 2 into omega into cos omega t minus omega square t into sin omega t. We can the derivative of this one is omega into cos omega t. Derivative of this one is, we can apply the product rule and we will get the final result like this. You can derive like. Okay, so what is L of f dash, f double dash? So we can put, instead of f double dash, we can put this one. So 2 omega into L of cos omega t. So that is 2 omega into s by s square plus omega square minus omega square into L of t sin omega t. That is actually function. So omega square into L of f. So from this you will get this is equal to s square into, we can take this function, from this formula. What is the formula? Yeah, this one. S square into L of f minus s into f of 0. F of 0 is 0, f dash 0 is 0. So the only term is s square into L of f. Okay. So that is s square into L of f. Okay. So from this you will get L of f is equal to what is L of f double dash? This one is the L of f double dash. So from this you can see that we can arrange this term. You can take this omega square into L of f to right side. So right side become omega square plus s square into L of f, and left side is 2 omega s into s square plus omega square, and from the right side omega square plus s square can be bring to the left side. So you will I will write that step. What is it? 2 omega. And we can move to the right side. Take that to right side. It will be like this. From this you will get L of f is equal to 2 omega s by s square plus omega square whole square. Okay. So that is the step. Okay. So one more problem is there. We consider f of t equal to cos omega t. Then f of t is equal to cos omega t. Then f of 0 equal to 1. F dash of 0 equal to 0. That is sin omega t. That is sin 0 0. F double dot of t is equal to minus omega square into cos omega t. And at t equal to 0, this will be minus omega square. Okay. So what is the formula? L of f double dash equal to s square into L of f minus s into f dash of 0, that is s into f of 0, that is 1. Then minus f dash of 0, that is 0. So s square into L of f minus s. So that, but directly we can evaluate the Laplace transform. That is L of f double dash is equal to L of minus omega square into cos omega t, that is minus omega square into L of f, because cos omega t is f of t. So that is minus omega square into L of f. So we can arrange this one as we seen in the word format. So what will be the common s square plus omega square L of f equal to s. So that means L of cos omega t equal to s by s square plus omega square. Okay. And the second function is g of t is equal to sin omega t. So what will be the g of 0 is 0, g dash of t is equal to omega into cos omega t. So g dash of 0 is equal to omega. Okay. So what is L of g dash? S into L of g minus f of 0, that is 0. Sorry, g of 0, that is 0. So S into L of g, that is omega into cos. No, directly we can see that what is L of g dash? Omega into L of omega into cos omega t, that is omega into L of cos omega t. From this you will get, we can substitute this L of cos omega t from this previous result. So L of g, that means L of sin omega t will be omega by s into L of cos omega t, that equal to omega by s into s by s square plus omega square, that is omega by s square plus omega square. I think you could understand these two problems, and we can understand these two theorems, and moreover you can do the problems in the exercise what we have discussed in this section today. That are some initial value problems, so that we'll discuss in the next class. After discussing some two problems in initial value problems, we will consider the exercise part. Okay, so that will be discussed in the next class. So we found two theorems on differentiation, derivatives, Laplace transformation of derivatives. Now we will discuss the problem Laplace transforms of the integrals. Okay, that will be discussed in the next class.